I'm going to start off today with where we left off yesterday, namely with the p-n junction. And yesterday we looked at the p-n junction in equilibrium and no biasing conditions. And today we will take it up from there. Yesterday what we had seen was that we can make certain simple calculations and show that the field, built-in electric field, is given by this expression. And from that we calculated that the potential V0 is given by an expression that involves acceptor carrier concentration, donor carrier concentration, the depletion layer width, and we didn't know it here. So what we did was then to obtain another expression that relates the built-in potential purely in terms of the acceptor carrier concentration, donor carrier concentration, and the intrinsic carrier concentration. This is something that is fixed for a particular material, and we know that, and so we can use this to calculate V0. And once we know V0, we can always go back to this equation here where we have an expression relating V0 to W0 and derive an expression for W0, which is what we had done and written W0 in terms of Na, Nd, and V0 and the permittivity of the semiconductor. Knowing then that W0 is expressed as the length of the depletion carrier, the width within the p-type side is Wp, and on the n-type side is Wn, and we have this expression. So with these two, we are then able to find out independently Wp and Wn. And we also had that in the case of what might be referred to as a p plus n junction, where that is when the acceptor concentration is much higher than the donor concentration, Na is much, much greater than Nd, we are able to simplify it down and bring it down to an expression W0 is equal to 2 epsilon V0 by E and D. This is the case of a P plus N junction as we saw it yesterday. So this is where we'll begin today, is to say, okay, what happens when we look at the p-n junction in forward bias? And we can realize simple terms that the p-n junction in forward bias means we've connected the p-type to the positive terminal and the n-type side to the negative terminal. And without going into great detail for the lack of time, we know that just as in the case of the Schottky barrier here, we are going to have a lowering of the barrier for electron transport from n side and for hole transport from p side into the opposite side. Primarily it is because now the field that is there, where we have a field that is existing, epsilon naught minus, E naught, whatever is the symbol that we are using for field, minus E. That means the built-in field is opposed by the applied field, and so we have a lowering of the barrier. And what that means is now there's a sharp increase in the holes that are going to be pushed into the n side, and for the electrons that are pushed into the p side. And this is called excess minority carrier injection. And as a result of this, there's a sudden change in current. Okay, so the lowering of the barrier has changed from E V0, we have changed it to E V0 minus V, where V is the applied bias. Okay, as a result of which we get an increase in current. Now these carriers that are diffusing in cross the space charge layer that we have, where there are no free carriers, and enter into the bulk of the n-type and the p-type respectively. The holes pass through the depletion layer and enter into the n-type bulk area, where they recombine with electrons. The opposite happens for the electrons that are injected into the p side. They pass through the space charge layer, enter into the p side bulk, and recombine with holes. Now because we are connected to an external circuit, the electrons that are recombining here with the holes that have been injected in are replaced from the source, and the same is true on the other side. And so we get a current that is flowing through the circuit as a consequence. Now to look at this a little more carefully, we can write that the whole current density for diffusion through this from here to the other side, we will write it as G D hole, a diffusion current due to the hole injection into the N side. I'm not going into the derivations and things like that. I'll give you some expressions that can be used, and then we'll go on. It will be given by E dH Ni squared by LH and D. Sorry. And exponential EV by KT minus 1. Okay? Excuse me. The diffusion current density JD related to the holes that are diffusing across there is given by E dH Ni squared by LH ND into exponential EV by KT minus 1. We've come across most of these terms before. Ni is the intrinsic carrier concentration. dH is the hole diffusion constant, which we saw when we were talking about what? In the case of the Schottky junction and earlier minority carriers when we were seeing, and the Einstein relations, we came across that. So dH is the hole diffusion coefficient. The one term that we haven't as yet introduced is LH, which is the hole diffusion length. So LH in this case is the hole diffusion length, and it is related to dH as root dH tau h. So we had dH as the hole coefficient, hole diffusion coefficient. LH is the hole diffusion length, and tau h is the mean lifetime, minority carrier lifetime, what we had seen, mean hole recombination lifetime. So that's the only expression, the LH, that we were not familiar with, that we did not have as yet, but it is related to two other terms that we already know. You may recognize immediately that this kind of an expression, LH is equal to square root of dH tau h, is common in all kinds of diffusion equations. That LH, which is in length, is equal to root dt. X is equal to root dt we find in all kinds of diffusion equations. So it's a similar concept there that we've used. So what we have right now is that under forward bias, we've got the hole diffusion current going from the P side to the N side. And a similar expression will be obtained for the electron diffusion current. Which will be given now simply replacing by the appropriate symbols for the electron. Exponential EV by KT minus 1. Okay? So in the case of the hole, we had JD hole is equal to E dH Ni squared by LH and D, and then the rest of that term was the same. For the electron, we have J, the diffusion current density for electrons is equal to E dE Ni squared by LE Na, where LE is again given by root dE tau E, as before, same as for the hole.
So what's in
What is?
Na?
Na is the accepted concentration. Have I used a different symbol before? I'm not sure. Is it ND and Na? Maybe I'm using a capital and a small, I don't remember, but Na is the acceptor concentration, ND is the donor concentration. So we have these two things which we can then combine. The total diffusion current density is then given as J is equal to JD hole plus JD electron. Okay, the two are summed up to give us a diffusion current, which we can write as J is equal to J S naught, combining some of the common terms there, and then this exponential EV by KT minus 1, where J S naught is going to be the sum of this term here for the electron and a similar term for the hole. J is equal to J S naught exponential EV by KT minus 1. And this equation is known as the Shockley equation. Shockley equation. Okay? And the expression for JSO then simply is EDH by LH ND plus EDE by LE NA, and we take the Ni squared common outside. Okay, so just the common terms that were there for the diffusion current related to hole and the electron. JSO is referred to as the reverse saturation current density. Okay, so that's the JSO. J is equal to JSO. It's a similar equation as we had earlier for the Schottky junction, incidentally. So don't get confused with the Schottky and Shockley. Shockley is a different person altogether. Okay. Now, we see that JSO, the reverse saturation current density, depends on doping, for example, ND and NA. I don't know what symbols I'm using. I hope I'm consistent. ND, donor. Yeah? Okay, ND and NA we have. So those are doping parameters, how I have doped the P and N junction. But it is also dependent on other things, DH, LH, DE, and LE, which are part of the lifetime is related to defects and so on. So not only how we doped it, but how good is the crystal is also part of it is coming in here. And then we have one other term it depends on, that is Ni. And Ni is related to what? Intrinsic carrier concentration. If you remember, it is related to Eg, right? Exponential minus Eg by Kt, Nc, Nv, whatever terms are there. So when the saturation current, reverse saturation current density is related to Ni, the implication is implicit there that it is also related to Eg, which is a material, what semiconductor I'm choosing. Okay, once the semiconductor is fixed, it also depends on the doping concentrations and so on. But there is an implicit statement here about its dependence on Eg. We can rewrite this equation to reflect that a little more clearly. So if we write that Vg is equal to Eg by E, so we are expressing the band gap in terms of the voltage there, then we can rewrite this equation as J is equal to J1 exponential minus EVG by KT. We are making a substitution for the Ni. If you look up the expression we had earlier for Ni is equal to in terms of Eg, and then Eg is substituted as Vg by E, we can make this substitution very easily and get J is equal to J1 exponential minus EVG by KT, and then the other term are, exponential EV by KT minus 1. Okay. Now when KT, EV by KT is much greater than 1, okay, that the applied bias is much more than the thermal energy, which is KT by E, which we saw was at room temperature 0.026 EV or so. So as long as the applied bias is larger than the thermal energy, the KT by E term, KT by E, then this equation, the one part of it will drop out as we saw earlier. So we can rewrite this equation that for this condition holding good, EV by KT greater than 1, that J is equal to J1 exponential EV minus VG by KT. Simply rearranging the equation and dropping the 1, which no longer becomes relevant because EV by KT is much greater than 1. So here we can see the explicit dependence on band gap, because EVG is the band gap that we have. So now we can take, incidentally, J1 that we have here is another constant that clubs together few other terms. So we can write J1, which is not the same as JSO, E DH by LH ND plus EDE by LE NA times NC NV. Okay, because now we have substituted for Ni in terms of NC and NV and Eg, so we get this expression. So now if we plot current versus voltage for different materials, that means as Vg or Eg changes, we will get something that looks like this. That's current and that's voltage. We'll get for different band gaps, we'll get a series of curves where this is, say, for germanium with a band gap of how much? Germanium? About 0.7 eV. Silicon, 1.1 eV. And gallium arsenide, about 1.4 eV. So this is the trend that we see as we plot this previous equation. J is equal to this term in terms of V and Vg. As Vg increases, or the band gap increases, the turn-on voltage here is going on increasing. So this is what we have written a term for current that is flowing under forward bias conditions that accounts for the diffusion of species under the lowered barrier. But there's another current term also that is related to recombination within the space charge layer or the depletion layer. You see, what we had earlier was that under the applied bias, excuse me, holes are going to be injected in here where they are now minority carriers, and they'll be recombining here, electrons injected in here, and they'll recombine here, and the circuit replenishes, the source replenishes these. But there is also some recombination occurring within here. Okay, that the electron that is injected in here and the hole that is injected in there, some of them will recombine. And it's the same source that is going to replenish these also. So we have to account for the recombination current, which is going to be different from the diffusional current across the space charge layer. And so we have to include an additional term for the total current to include this recombination. Writing the recombination current as J recom, we have then as expression J is equal to JR0 exponential EV by 2 kT minus 1, where JR0 is equal to ENI by 2 WP by tau E plus WN by tau H. There's again some constant term there that is not dependent on voltage, and we have this additional term. So now we have a term that is related to recombination within the space charge layer, that is over here inside this region. That's your metallurgical junction, holes being injected in, an electron being injected in, and we have recombination within the space charge layer. So these two terms, J recombination and J diffusion, which we just got earlier, we can combine together. And what we will get then is J is equal to J, the diffusion current, plus recombination current. This will account for the total current under forward bias, which, as we saw earlier, was JSO exponential EV by KT. We are using that the approximation that EV by KT is greater than 1, much greater than 1, so we've dropped out some of it, plus JRO exponential EV by 2 KT. Again, the one term is dropped out of the picture. So we'll use that it's greater than KT by E. Okay? One way to look at this whole equation is to rewrite it as J is equal to some other term that is independent of voltage, and club it all together as J is equal to J naught exponential EV by N KT. The fuller expression will include a minus 1 there. So again, for the approximation for V greater than KT by E, it is EV by NKT. Otherwise, you've got EV by NKT minus 1. What is N? N is known as the ideality factor of the diode. N acquires a value of 1 when the current is limited by diffusion of minority carriers. Okay, in the neutral region. That's the first, it's limited by JD. And N has a value of 2 when the current is limited by recombination in space charge layer. So we can make a plot on a log scale. We have here the current. So log I versus V, if we plot. For germanium, for example, we will see something like this on a log scale, where N is equal to 1. Okay? That means in germanium PN junction diodes, the current is limited by the diffusion of minority carriers. On the other hand, for gallium arsenide, we will see something like this with N is equal to 2. If you look back at the previous equation, you will realize that if you were to plot in terms of the log of this versus V, you're getting N is part of the slope there, right? And then in the case of silicon, it has some interesting behavior that it starts off as 2, N is equal to 2, which means that it is due to space charge layer recombination. And then the slope changes. So here the slope is N is equal to 1. Whereas at lower voltages the slope is N is equal to 2. So that means in silicon we have that the slope, the current is limited initially by recombination in space charge layer, and at higher voltages it is limited by diffusion of minority carriers. What is this part here? Where we are beginning to see the series resistance, that is the resistance of the bulk of the semiconductor itself. Ultimately, all these diodes, the current will be limited by the resistance of the series resistance that is there for the semiconductor. So if we took all of these curves high enough, we'll see them being limited by series resistance. Now we have one situation that for silicon, N is equal to 2 may extend all the way up to the point instead of changing to N is equal to 1 for highly doped diodes. So that could be a variation that we may see that it becomes like this, and that would be true for very highly doped diodes. Okay? But this is the difference between N is equal to 1 and N is equal to 2, two different mechanisms that limit the current in forward bias. We'll look at the junction in reverse bias, where basically we connect the P side to the negative terminal of the source, and whatever is our bias is VR. In this case now, my built-in field and the biasing field are acting in the same direction, so I get a stronger field action there. And that means that the barrier height is increased from EV0 to EV0 plus VR. Similar idea we had for Schottky also. The depletion layer becomes wider now because here there are holes and here there are electrons that are now attracted by the negative, positive voltage here and the negative voltage here, and so they expose a larger amount of the fixed charges here. Okay, because more of the electrons are pulled out here, so the depletion layer width has increased in this case from W0 to some value W. It has increased. The current flow that we have under such circumstances is for two reasons. One is very much like the Shockley model we have, namely that minority carriers can now go from P side all the way through the space into the space charge layer here, where this built-in field will separate them. So again here we have minority carrier from bulk into space charge layer, where they are separated by the field, or they drift under the field. And the same is true for injection of electrons in there. They will drift under that. So it's a very similar thing like we had for the reverse saturation current for forward bias. Same Shockley model can be applied here, except that we have now, instead of J, what was it, S naught, we now have minus J S naught. That will be the limiting. That's why we use the term in reverse saturation current density for J S naught, because that is the limiting current that will flow due to injection of carriers. And we have an expression for that. In addition to that, the second reason why current will flow is that there is thermal generation of electron hole pairs within the space charge layer. And when they are generated there, some bond is breaking due to thermal energy. Because the space charge layer, there is a built-in field, so that will separate out the two carriers that are the electrons and the holes that were generated thermally. So we're going to get a current contribution due to thermal generation, which we will write as J gen. And an expression for that can be expressed in terms of E W Ni by tau G, where W is the increased width of the space charge layer. Okay, we have a larger area, and tau G is some kind of a thermal generation rate, the mean time to generate 1 EHP. Within the space charge layer. And we already have an expression for Js naught. So the reverse current can then be written in terms of these two. It is Js naught plus J gen. And using the expressions that we had earlier, EDH by LH ND plus EDE by LE times Ni squared, which was the expression for Js naught, and we just had an expression for J gen. So this is the reverse current that we have.
So shouldn't it be minus Js naught?
What is it?
So shouldn't it be minus Js naught? You pointed it right.
Yeah, but then all the voltages will be different here. When we put in I mean, in magnitude, yes, it is. Sorry, in sign, yes, it is. It is flowing in the opposite direction. Magnitude is the same,
Yeah,
and the direction of this current will also be the same. Okay, so that's why they are. What you're saying is correct. I mean, when we look at the plot, the current is going to be negative side. The flow is in the opposite direction to when we have in forward direction. You're right. But when both these currents add up,
both of them are
in the same direction. So that's why I've written it both as plus. But the actual sign of it is flowing in the opposite direction to the case of forward biasing. You're correct. This term here is dominant at lower temperatures. Okay. Diffusion, all that becomes rather small. And then it is, remember, in both of these, it is related to this Ni and Ni squared we have in both of these terms. So in this case, it is at lower temperatures, we will see a domination due to thermal generation in the space charge layer. So what this curve I just started plotting, we can plot it. If we look at I versus V, I switch between I and J all the time, but it's obvious that one is related to the other through the area. J is the current density and I is current. If you look in the forward direction, currents of the order of milliamp will flow, and we have an expression there, I is equal to I naught exponential EV by NKT minus 1 if we are taking the full expression. Right? In the reverse direction, what we have is that I'm plotting it on the same scale. except that here now, I mean on the same graph, the scale is different. Here we're talking in nanoamps, here we're talking in milliamps. So the magnitude of the reverse current is very, very small. It's only in nanoamperes. And we will see that the term that we had for Js0, for values that are greater than the kT by E, it is independent of voltage. Okay? If you go back and look at the terms that we had in there, what all it depended on, Js0, we don't have a voltage dependence beyond that initial pickup there. It depends, of course, on Ni and Na and Nd and so on, but not on the voltage there. But the current that we have due to thermal generation is actually larger in magnitude. I drew it wrong, sorry. Something like this. This is the J gen current. Both of them very small in magnitude compared with the forward current, but these account for the total change that we are seeing when we move from reverse bias to forward bias. Now you can compare this with the Schottky junction. The curve looks rather similar. What's the difference between the two? All right. What else? I mean, both of these, maybe one or the other dominates. It's not that both of them will be drawn like this. Let's say one is dominant. Let's say that's all you have.
It's constant. It's independent of voltage.
That would be more or less true for Schottky also. The primary difference we see is that in the case of PN junctions, it involves minority carriers, injection of minority carriers, and then in Schottky case, there's no minority carriers involved. And that's what makes Schottky diodes faster, because when you switch in various applications, you go from one direction to the other. It is the movement of majority carriers that is involved there, not minority carriers, which slow down the whole process. Charge storage, when it is going from one side to the other side, you're flipping back and forth in biasing. The Schottky diodes are much faster than the PN junctions because it does not involve minority carriers. There are other differences too. With PN junctions, you can usually go to much higher breakdown voltages and so on. There are pluses and minuses. But you have to recognize that the PN junction involves minority carriers, whereas the Schottky junction does not involve any minority carrier transport across the junction. What we can do is to express it, the whole idea that we have so far got in terms of the band picture. I'll draw three simple band diagrams. At V is equal to 0, the zero bias, I really didn't draw that as we did for Schottky. We've got no bias conditions. First of all, the simple thing we know is that the Fermi level is the same on both sides in equilibrium. And so we can plot it in terms, on the P side, it's close to the acceptor, to valence band. On the N side, it is close to the conduction band. And then for the same band gap, so we have EC, that's E, Fn, EV, EV on the P side, EFP. And that's now my W0. Somewhere in there is our metallurgical junction labeled M. I'm not going into the where it might be and so on. Okay? And here now our built-in voltage, built-in potential is EV0, which is now at equilibrium. No further flow of electrons or holes in either direction. This part is the space charge layer. This area has got what we call the neutral N side, or the bulk of it, and the neutral P side. Now if we show it in forward bias, we have now that the barrier has reduced to be EV0 minus V, and the Fermi levels that we had are no longer coinciding. It's not in equilibrium anymore. And the gap between the Fermi levels here is equivalent to the applied voltage EV. So here, because of this lowering of the barrier by EV naught minus V, what I discussed, I'm just putting it together again graphically, we have now that electrons can flow over this lower barrier as a consequence. And the same would be true for holes, they can flow in the opposite direction. Then we take the third case where we have, and the field and all you know, the field will be reduced from epsilon naught to epsilon naught minus E. Okay. For V less than 0, that is some reverse bias that we have, now we have that it has increased the barrier. Depending on how much you have, I should have been careful in drawing this, you will notice the Fermi levels now. EV here, it's real. I'll have to make use of this diagram later, but EV is now higher than EC. It's got a very practical implication, which I'll come to very shortly. But at low bias, reverse bias voltages, this will not be the case. You'll still be a little lower here. Okay, you haven't as yet gone so that EV is above EC. Okay, you can probably guess the implications as we come to it, but for now, we'll leave it that. Just pretend as if EV is less than EC at this point. We haven't gone to that higher voltage. So in other words, this change hasn't been as much as I've shown it. Because if this is true, then something else is going to happen, which I'll come to in a second. Okay? So this is the situation in reverse bias, probably just a little smaller than what I've shown. The field is now enhanced from the built-in field. The additional applied field is there. In addition now, my depletion layer width has increased significantly from W0 to the term W. We can discuss one more thing, is that if you remember, inside this depletion layer, what do we have? What is there in the depletion layer? Fixed charges, right? Obviously, by the name depletion layer, we are implying that there is no free carriers in there under equilibrium. It's the fixed charges. And when you have fixed charges like that, what can you expect? You got a positive, you got negative charges. You got a dipole, capacitance, right? It's charge storage, fixed charge stored there. It's capacitance. So we talk in terms of depletion layer capacitance, where capacitance of the depletion layer is defined as dq by dV. So these are the charges that are stored within the depletion layer. We had this expression for the depletion layer width in equilibrium, 2 epsilon Na plus Nd V0 by E Na Nd to the power half. This is what we had under the open circuit, no biasing. Now when we bias it, we've got W, the same expression except that it's going to be V0 minus V. So you can see that in forward bias, W will decrease, whereas in reverse bias, because V is negative, it will add on to this, and we'll have the increase in depletion layer, as I mentioned earlier. Now what we are going to do is to look at, we want an expression for the charge stored in terms of voltage, and then if we get that in the depletion layer, then we can differentiate that to get the depletion layer capacitance. Earlier we saw that the charge stored in the depletion layer on either side of the junction could be expressed as END WNA. I had left out the A because I said area is the same on both sides. If you remember, ND is donor concentration, how many per centimeter cubed, and when you multiply it by E, you get the charge per centimeter cubed multiplied by a volume, which is the area times the thickness of the depletion layer, which is also the same for on the other side, NaWP, and the area is the same. That's why I left out the area in the previous equation. We also know that W is equal to Wn plus Wp. Okay? So I can write Wn here from this equation is equal to Q by ENdA from this equation. Q is equal to ENdWNA. And I can write that Wp is equal to QENAA. And so we can have an expression for W, the total, as equal to Q by EA times 1 by ND plus 1 by NA. All right? Which you can obviously write in terms of ND plus NA by NA and D, this term here. Okay? And now I have an expression for W that I can go back and use. You see, we just had a term here that related W to V. And now I've got W here in terms of Q. So if I replace W in that equation there, we will get then that Q, I'm replacing W simply by EA times NA plus ND by NA and D, which is just the expression for W that we obtained just now here, is equal to the expression that we had for W, 2 epsilon NA plus ND V naught minus V by E NA ND, the whole raised to the power half. You can play with this equation, rearrange it, simplify it, and then you can differentiate Q dQ by dV to get the depletion layer capacitance, which turns out to be A by V naught minus V to the power half. That's the only term that's getting differentiated really. E epsilon NA plus ND divided by 2, I'm sorry, NA ND, not plus. In the denominator we have NA plus ND. This is simply NA ND to the power half, which is very similar to the expression for a parallel plate capacitor, except that our W, this is the expression simply for a charge stored in a parallel plate capacitor. It's proportional to the area, inversely proportional to the separation between the plates and the permittivity. That's the basic idea. So here also you've got the area, the permittivity, and then you've got a W term, which itself is dependent on voltage. So W is proportional to V naught minus V to the power half. That's so so the junction capacitance in the depletion layer is behaving very much like a parallel plate capacitor. So we can now make a plot of capacitance versus voltage. And what we have is something like this. That's in forward bias, and that's in reverse bias. As we increase the reverse bias, the effect is really to cause the charges to be farther apart, the field that is there, and so we get a decrease in the capacitance. This is a useful plot. We are able to actually measure these kind of things for APN junction, measure the capacitance versus voltage behavior and from that we can extract useful information. One way to do that extraction is to take a look at that equation for capacitance and rewrite it in terms of 1 by C squared. All right, we had an expression that was C is equal to something to the power half. If you write C squared and then take 1 by C squared, we will see that 1 by C squared is equal to V naught minus V by A squared 2 Na plus Nd by E epsilon naught Na Nd. Simply transposing it 1 by C squared. Now what would happen if we were to plot 1 by C squared versus V? What could we expect? A straight line with a negative slope, right? So we would see something like this. And what is it that when C's, the capacitance, or this 1 by C squared term is equal to 0, which is at this point here, what is this value of V? V naught, right? So here I've got, by plotting, measuring the capacitance as a function of voltage and then plotting it as 1 by C squared versus V, the x-intercept where it cuts the x-axis is my built-in potential. And related to the y-intercept and the slope come these parameters, Na and Nd. Okay, so if one is larger than the other, so you've got a P plus N type of junction, or even this is true, you can plot this for a Schottky junction, you would get the value of either Na or Nd, depending on, if it's Schottky on an N type, we will get the value of Nd. If it is P plus N, we will also get the value of Nd. So this is a useful, very useful technique that we can make use of to determine the parameters of the particular diode that we are studying. The voltage dependence that we saw for capacitance is made use of in devices known as reactor diodes. They make use of the voltage dependence of the capacitance. Basically, by operating these in reverse bias, we limit the current. There's very little current flow. But by varying the reverse bias voltage, we change the capacitance. And what this is made use of in a practical application is that, say, in tuning circuits, I need to have a sort of a variable capacitance in there to adjust for, say, changes in the load and so on. And what this will do is simply by varying the voltage across this diode, I get the variable capacitance. And we are operating in reverse bias, so current doesn't flow through, very little current flows through such a device. Now I'll come to the last sort of topic related to PN junctions, namely breakdown phenomena. I hinted at that when we drew the reverse bias picture. I said something is odd there, and that's because at that point we are already into the breakdown region, the way I drew it. All right, we'll come back to that. If we go on increasing the reverse bias, at some point the diode is going to break down, and there are two reasons for that. One is known as avalanche breakdown, and the other is known as Zener breakdown. Now what we see in such a case, just looking at the reverse bias, is that the current is very low up to a point, and then all of a sudden we have something like this. The current increases drastically beyond some reverse voltage, say VBR, which is negative. So at some point, all of a sudden we get an increase in current, and that is related to these, one of these or both of these mechanisms. What would happen if the current goes on increasing like this? What would happen to the device? Why? All right. It's a temperature related thing. I increase the current without limit. When the current increases, power dissipation, then there is heating, And the hotter it gets, eventually I may usually destroy the contacts or something, and that's the end of the device. But in and of itself, if I can limit the current to some safe value, then even if it operates in the breakdown mode, nothing will happen to that. And this is made use of in voltage clamping circuits, okay, where you can limit the current by an external resistor so that the current doesn't increase beyond a breakdown point, beyond some burnout point, but you're able to clamp the voltage. It does not go anywhere much beyond VBR, more or less stays in the VBR range. So this is a practical application that you can make use of even breakdown phenomena where things are falling apart. Now we look at quickly at these two, avalanche. As the name implies, it's sort of like snowball rolling down a mountain. That's the meaning of avalanche, if you know, right? There was an avalanche in the mountains, so the climbers, they died. Something falls, that picks up more, and so on. And basically it's related to the fact that as we increase the reverse bias here, the field is increasing. Slight changes in V cause the field to change significantly. So now the electrons are going to be accelerated much faster. So they pick up energy in transiting through the diode. And this acceleration ends up that they will have enough energy with the increased field to go and knock another electron out from its position, basically to start breaking bonds. That's what we mean when we say an electron is excited from valence band to conduction band. So where we started with 1, we ended up with 2 electrons now, and the process will repeat, and in a very short time we are out of control. It is rapidly increasing, and so on. Of course, this is not the exact picture. I'm just giving you a rapid idea. This is how. So all of a sudden now we've got so many electrons, and that is really what is happening in avalanche breakdown. There's one term called multiplication, which means that if under reverse bias conditions where you did not have this breakdown, if the current was I0, under reverse breakdown conditions where we have avalanche breakdown, now the current has been multiplied by this term M. So it's a multiplicative effect, where M is given by 1 minus VR by V breakdown to the power an exponent n, where n can vary between 3 and 5. And very quickly, the Zener breakdown. I'll come back to the figure that I drew to just simply make use of it and conclude here. Namely that if we have enough of a voltage in a heavily doped diode, this example, if the doping is heavy, we recognize that the depletion layer width is small. Okay, so W is rather small for a heavily doped diode. And what that means is that if we achieve a reverse bias voltage where we have in this situation that the valence band is higher than the conduction band here, we will get tunneling through here, because this is all full of electrons, these are empty relatively, and the depletion layer width is small. So tunneling current is there, which is more than the other current that we have in the regular reverse direction, and that can lead to Zener breakdown, additional current flowing because of this tunneling in heavily doped diodes. Okay, these are two breakdown phenomena. They operate in different ranges. In heavily doped case, 10 to the power 19 and all, it's Zener. In the other cases, you'll find avalanche breakdown is predominant. Okay, we'll stop here. We'll take up some other types of devices in the next class, and then conclude this topic on semiconductors.